All right, we're going to pick up with E1 mechanisms and reactions, and here we're looking at these compounds a little differently because we are now thinking about waiting for that leaving group to leave instead of trying to identify a strong nucleophile. Now we have to have a weak nucleophile so that this has a chance to leave on its own. This first step is going to be rather slow because we're forming a relatively non-stable carbocation intermediate. And then after that carbocation is formed, the leaving group has left, the weak base will attack that acidic hydrogen on the beta carbon, and the electrons holding that hydrogen on are going to form that double bond as shown here. Here I'm showing you the reaction coordinate diagram for an E1 mechanism, where again the rate is only limited on the concentration of the alkyl halide and not the weak base. So we can see that first activation step is the highest energy step, that's the rate limiting step for the formation of that carbocation intermediate, and then that second step can quickly move down to the remainder of the products. So in this, you will want to draw the mechanism out. If you want to pause it right now, that's great, and then I will draw it out in a second. The first step is, remember, we want to show that intermediate, and in order for that intermediate to form, the first step has to be, that first step is going to lead to an intermediate that is going to leave us with a carbocation. So this chlorine group is going to leave and leave us with that positively charged group. Now I can see that double bond is forming between this alpha carbon and beta carbon. So I know that the hydrogen is attached to that beta carbon. That's going to be attacked by the base, and I have a weak base here, so it's not charged, that is going to bond to that hydrogen, and the electrons in that beta carbon bond are going to flip down and form that double bond at that location. The rate of an E1 reaction is consistent and matches that of the increased carbocation stability. Because again, this is the first rate limiting step. This has to happen, so the more stable it is, the quicker it's going to happen. Tertiary carbons are much more quickly to react via E1 than primary carbons. Again, looking at identifying those different beta carbons and if they're secondary, primary, tertiary, the same way with E1s, the more substituted that carbon, the more major the product is going to be. For example, here, this red beta, right, these two beta positions are equivalent. This is going to be a 1, 2, 3 tri-substituted versus with the blue beta, it's a di-substituted. So that's going to be the minor product versus the tri-substituted, which is the major product. The solvent here also plays a role if we're looking at protic versus aprotic solvents. Again, the rate doesn't include the base at all. And we're going to look at also the strong interactions you can see here. These are all weak nucleophiles or weak bases in addition to the leaving groups, right? These are going to weaken these and slow these down and allow the leaving group to leave and the leaving group to be more stable once it does leave. Where aprotic solvents kind of leave these alone a little more and allow these to interact and act as stronger bases or less stable leaving groups. So you can kind of think about this is the opposite of E1, where we want to have the protic solvents that can have stronger intermolecular forces with our bases and our leaving groups for this mechanism. Again, an overview on this mechanism. The rate order is only going to be based off of the alkyl halide, and it has that intermediate step followed by the completion. So there's a two-step mechanism. The more substituted, that reacts more quickly. Again, similar with the E2 chemical reactions, bases are favored by having weaker bases to allow for that carbocation to form. And then we have better leaving groups make this happen faster because, again, intermediate is a carbocation. That leaving group has to leave first. So the better the leaving group, the more quickly this reaction will occur. And then polar protic solvents are going to help to dissolve not only that leaving group and have the high hydrogen bonding intermolecular forces, as well as to make that base more weak and not interact before the leaving group can leave. Here I'm going to show you an E1 reaction using Zaitsev's rule to predict the product, but maybe try it first, pause, and then start from there. In this A reaction, right, the first step is to lose the halogen. So we're going to write that out first. And we know that that's going to form the carbocation on this alpha carbon. So we have beta on this side, which is equivalent to the beta on the right side. And then we have another beta that is not equivalent. And we have this is a primary carbon versus two secondary carbons. So we'd expect the major product to form a double bond between the two, the more substituted carbons. So I'll redraw this out and we'll draw a double bond there. For B, we're going to redraw the carbocation intermediate as well. And we're going to, I'm going to just remove, right, so we have the electrons leaving here, didn't draw those out first. That carbocation is going to form here at the alpha carbon. And we have, again, different possibilities. So we have a beta 1 for the primary, a beta 2 for the secondary, and here's a beta 3 for a tertiary carbon. And so we would expect the more substituted carbon would form that double bond, and we'll draw that out as such, and that should be our other product. Here's again kind of that overview idea, what happens with changing different variables within an chemical reaction for SN1, E1, E2. And so if we're going to double the alkyl halide, that should double the rate at which the chemical reaction occurs. Now remember, the rate doesn't include base for an E1, so this will do nothing. If we put as much base in there as we want, it won't change that rate of the E1 reaction. If we do change this halide from CH3 CBr, so this is going to be a tertiary carbon at which the bromine's on versus a primary, that is actually going to be a slower reaction because it moves from a tertiary to primary halide. So there's going to be less substituted, slower chemical reaction. The leaving group from chloride to bromide, we know that bromide is a larger, more stable ion, so that will be a faster, better chemical reaction. Changing the solvent from DMSO to CH3OH. DMSO is aprotic, CH3OH is protic. So we're going to increase, it's going to be a better chemical reaction because we're going to better dissolve the leaving group, have intermolecular interactions, and potentially weaken the base as well to allow for that leaving group to happen. So how do we choose between substitution versus elimination reactions here? So one is with the substitutions, we're considering this group that's coming in to attach to a more positive element, the nucleophile, right? So we're going to attach to that carbocation versus a base that's going to attach to a hydrogen, and then the bonded electrons are going to form that double bond. So that's really the difference here with the terminology, where you're going to use nucleophile if it's attacking a carbon, we're going to use a base if it's attacking the hydrogen. So typically both of these chemical reactions has capacity to occur because, again, the rate limiting step is the formation of the carbocation. So this is the first step for both of those reactions. And then it's just a matter of if this is going to act as a nucleophile and attack the carbon, or act as a base and attack the hydrogen. So both of these products, you can form the SN1, and the elimination product is typically a minor product, but it usually comes with that SN1 product. So here's just a question to practice to draw both the SN1 and E1 products for the chemical reaction. So feel free to pause if you want to practice this before I go through the solution. The first step is, of course, going to be generating that carbocation intermediate, and then we're going to determine if we're going to treat water as a nucleophile to come here, or we're going to treat it as an electrophile to come here and to form our double bond. So those are our two different options. For the next one, of course, we're going to do the intermediate again. Are we going to treat it as a nucleophile, or are we going to treat it as a base? Now we want to compare different elimination reactions, so E1 versus E2. So the E2 mechanism, of course, we're going to be more useful because it's going to happen much more quickly, and we can have a better prediction of how quickly this is going to happen, and we can generate more of the product, whereas the E1 mechanism's generally going to be the minor product of the SN1 setup. So because of that mixture, we're going to get mixes of different products out. So we're going to obviously favor that strong nucleophile in this instance, or negatively charged bases, and especially OH or OR negatively charged groups. And this occurs quicker on the order of reactivity. Of course, the more acidic hydrogens that are available, the faster it's going to happen. So R3CH-CX is going to happen, or tertiary halide versus a primary halide is going to happen more quickly. So in this type of problem where we're looking for E1 versus an E2, one of the first things to look at is to look at the base that we're looking at here. So this is strong, strong, weak, weak. You have a good leaving group here, a good leaving group here, not as good of a leaving group here or here, right? So you have to look at the leaving group, and then you have to look at the tertiary carbon, secondary carbon, primary carbon, tertiary carbon. So those are all going to play a role in which way this is going to go. For this first one, the tertiary carbon, we know that these are going to be stable carbocations, but we also know that E2 reactions can work here. But because this is a strong base, this is going to favor E2. For B, it's a good leaving group. We also have a weak base here. So then we're going to have to look at, this is not a bulky base, and this is going to be able to interact relatively easily. So we would expect this to go through the E1 mechanism, the weak one, E1. Again, there is going to be some SN1 compound as well in there, because there's always with E1, some SN1 is actually the major product. For C, we are going to have tertiary carbon, good stable carbocation, a weak base here, so I would expect that this would go through the SN1 E1 mechanism. Right, this is specifically asking about E1 or E2. Here we have a primary carbon, and that just right off the bat is going to be a bad carbocation. So and in addition, here's a strong base, so we would expect with that primary, really the only option is the E2 reaction here, or an SN2, but right between E1 and E2 we're going to get E2. Here's an overview of the alkyl halides and the difference between SN1, SN2, E1, and E2 mechanisms. I think the first step is to always look at primary, secondary, tertiary halogen or alkyl halide, and that'll help you decide if you're going to look for more of a SN2, E2, or an SN1 or E1. The next thing is to look at the nucleophile or the base. If it's strong, it's going to generally be going through an E2 mechanism, right, for the primary, and for the tertiary, if we're talking about a strong base, we're going to have an E2 as well. And with weak bases, if the primary we don't get an SN1 or E1 are not an option, but the tertiary it is if you have a weak base or a weak nucleophile. And for the secondary, you can have all of them, right? So these are all options, and it really depends on the base, the solvent, and so those are what are going to dictate if you're talking about E1 SN1 for the weak nucleophile or base, and then with strong bases or nucleophiles, you're going to have the E2. So for this question, I'd like you to think about, pause again, draw out the products for the following reaction, and start with classifying the alkyl halide, look at what possible substitution products, what possible elimination products there might be here. So in order to begin this problem, right, I'm just kind of doing the same thing, except for over here, now I've labeled the alpha carbon, the two possible beta carbons. Here on the other side of this bond, I can't have a beta carbon react because it is a quaternary carbon. There are no hydrogens available to react here. So those are my only two options on these two beta carbons shown here. The next step is to figure out, okay, so what do I have for my my alpha carbon is going to be tertiary, right? Tertiary alkyl halide. I have 1, 2, 3. So that means that we actually have quite a few options here. We can go through an SN1 or an E1, and an E1 I should say, so both of those chemical reactions are going to occur, or an E2 depending on the base. Here we have water is a weak base, so we're going to expect this to go through an SN1 and an E1 chemical reaction. Here are the possible products. We're going to be doing a substitution, is going to have the hydroxide substitute for that bromide, and the E1 product is going to go onto, it doesn't matter, these are both equivalent beta carbons, so we'll have a double bond for that elimination reaction. Do the same for this reaction now. Pause here, otherwise I am going to continue on. For this reaction, we have a alpha and the beta at equivalent positions on either side. We know that this is a secondary carbon, so we'll be looking at this group here. The next thing we want to look at is the base, which is a strong nucleophile and base. So these could go through the SN2, E2 chemical reactions, and so these are, the products are going to have either replacing the bromine with an OCH3 or having a double bond on either of those, between those alpha and beta carbons. So this will be a good practice for the quiz on Monday. Practice working through these different products for each of these reactants, looking for the differences that will allow you to determine if you think this would go through an SN1, E1, SN2, E2 chemical reaction.